Thanks for being here. How many of you write code? Okay, and in large teams, or have ever done it in larger teams? And how many of you have been on a project that's failed? Okay. How many of you have had the majority of your projects fail? Maybe you don't. Okay. It often happens. You shouldn't feel upset about it because you're not alone. Something like 93% of software projects are challenged or failing in one way or another. There are different studies on this, so you get different numbers when you run them. But only in this one study, I saw around 6% of projects were successful when you define it as landing on time, within budget, and delivering the functionality you're setting out to deliver initially, right? About half of them are challenged on at least one of those dimensions, and then 40% of them fail to get out the gate at all, right? They are completely written off before they are shipped to end users, and so that's just a complete sunk cost. Now, often people, when they're trying to understand why these things are having problems, they reach for, it's a team issue, it's a person issue, it's a leadership issue. That's the first thing that you go at. These people are idiots, we got to fire everyone. The next thing that they do is they say, okay, there must be a process problem, right? They are not, send everyone to Scrum Master training. That's going to fix everything, right? We're going to make them have stand-up meetings and pair programming and sprints, right? And that's going to fix it. But often there's the underlying root cause of these project failures. What we found through our research is the underlying software complexity of the system. And we're going to unpack that in two different ways. But we've done a lot of work to measure software complexity inside code bases of various sizes and ages and languages, and statistically connect that to developer productivity, to defect density, to even things like staff turnover. Turns out that if you're in a terrible code base, you quit or are fired more often, right? So I'm going to show you how we have been measuring software complexity in these code bases, how we've statistically connected that to business outcomes, and then how we can use predictive analytics to say what you should do with the code base moving forward. Often, if you have a large portfolio of software code bases, you have a lot of systems that should be retired, but no one wants to pull the trigger on them, right? So we're going to go through the logic of how you can decide that across a software portfolio. Now, if you look at software development projects, the blue project is what you would want, but often we see something like the orange project above it. You'll have development going on over an extended period of time, well beyond where it should have been. Then your sustainment costs or your maintenance costs go sky high, and then you might have an abbreviated, shortened lifespan that happens rather abruptly as the thing kind of crumbles under its own weight. Often that's the point where a company fails or a project fails. Now, these systems fail when they're in operation too, right? We see every day you can open the Wall Street Journal and there's some chance you're going to see some software failure in there, whether it's a braking system failing or a stock market crash caused by it. These things happen regularly enough that we don't really think about them too much. It's in a constant state of, I wouldn't call it crisis because we're all still alive, but it's a constant state of problem. And one of the reasons for that is that software is one of the most complex things that humans have ever set out to create. One of the problems that we have as software developers is that the human brain evolved to process three-dimensional information, to have an intuitive understanding of physics and mechanics. And so 60% of your brain can be brought to bear to understand a mechanical system, like the Apollo 11 lander that you see there, right? If there was rust on that system, right, the mechanic and the receptionist and the CFO could have a useful conversation about the need to eliminate the rust on that system before it flew. Software has structure, but it's not three-dimensional, so you can't see it. You can't bring that part of your brain to bear. So if you try to have a conversation inside a software development organization with the CFO and someone on the machine floor about the need to eliminate the equivalent of rust, you're going to have a much harder conversation, right? Now, rust is like code quality, right? Let's think about architectural quality. If one of those legs was bolted to the top of this thing, you would also be able to have a useful conversation about the need to fix the design of that system. Similar in software has design, but you can't really see it, so it's hard to have useful conversations about that across domains and across the business and the technical side. And that's why technical debt probably accumulates a lot more readily in software, because people don't have the ability to have those conversations they need to have about eliminating it. Now, the problem is harder than that. Now, Margaret Hamilton was the woman who designed the software that went into the Apollo 11 lander. She's standing next to that stack of code. Those pieces of paper is a printout of the code that went into the lander. Now, if you look at some of the systems that we're looking at today, you got 100 million lines of code. We've taken the picture of Margaret here and multiplied it by 1,500 and kind of shown you this grid. And you have all these interconnections between all of the different pieces of code flowing throughout this entire organization. If you took that stack of paper next to Margaret and multiplied it by 1,500, you'd have a stack of paper that went 1.5 miles into the air, right? So this is just to show you the raw amount of complexity, detailed complexity and structural complexity in your systems that we have today. There's no human on Earth who is capable of understanding what's going on in some of these code bases, right? That's true of a lot of our complex systems. There's no human being on Earth who understands why a Boeing airplane stays in the air either, right? There are too many parts, they cross too many domains. It's a little scary, but that's the modern engineering challenge. How do you build things in such a way that they can function even though no one knows why, right? And software is everywhere, which is something that we all know. So how do we think about what we can build into these software systems to make them function even though no one really knows why? Well, one of the things that we worry about is code quality. These are two versions of Hello World, right? And you're going to hope that your contractors are giving you the blue version. The red version is actually, I got it from the one of the obfuscated coding competitions, but that's Hello World. And often if you look inside a software system, you'll find plenty of procedure 2s sitting around there somewhere. But that's only half the story, and this is actually the easier thing to fix in a code base, because as soon as you identify it, you can tell one person to go fix it, right? What's harder are the design challenges. So let's think about, this is a video game company that I was working with many years ago. And in a video game company, you have an engine. And your engine is a platform upon which you build code that goes into individual games, but it's reusable code that you can leverage for economic benefit. And in this engine, there's a physics subsystem, a rendering subsystem, Xbox drivers, PlayStation drivers, and then you've got the game code. It was a very violent game, so it had weapons and bad guys, right? But when we first scanned this system and looked using graph theory at the interrelationships between the parts in that system, what we found were a bunch of places where there were calls from the engine up into the code implemented inside an individual game, right? Which is not what you would expect. So we immediately went to the leadership and said, okay, why am I finding hundreds of these places where engine code is calling into game code? That seems like a violation of architectural principles. I want to have layering in this system, not a circular loop. Well, they said this was technical debt. It saved them a month about 3 years ago. They did it knowingly. What they should have done was said, hey, that algorithm that's really useful in the game, we want to factor it out, pull it down, broadcast its presence to the rest of the organization, and made it available to all. But they saw some useful bit of functionality implemented in a game, and they just called it because it was there and it was useful and saved them time. And they never paid it down. So what happened as a result of that is that 3 years later, this team, Game Team 1, makes a change to their code base, and it improves their code, and they have no reason to believe that it's going to cause a problem somewhere else. But it does, because that patch, along with hundreds of other patches, gets merged into Game Code 1, gets sunk down into the engine team, gets merged with hundreds of other patches from the engine team, and then all of a sudden they land on Team 2's doorstep, and this causes a side effect or a bug. They now have to debug it. Right? So if you're an engineer, you know that the first thing you do is you blame yourself. You try to debug it in your own code, because it's really embarrassing to go blame someone else and then realize that it was really a bug in your own code. So they spend a month doing that. And then they realize, okay, it's in the engine, right? So now we have a cross-functional team across an ocean, and they spend time trying to diagnose, is this a side effect, the interrelation between the two, or is this a problem with the engine? And then they come to realize, okay, this is something that was implemented by someone in Game 1 who is no longer with us, and now we're approaching Christmas, right? Now, if you're a video game company that ships all your games in January, that's really bad, right? And that's what they were facing. because we're getting to the point where you're approaching a Christmas release. So now what they have to do is they have to backport to an old version of game 1, backport to an old version of the engine, shoehorn that into game 2, and pray on Christmas morning that this thing isn't going to collapse, right? Now this is bad. This is really bad for a company, and this is what we would call a design flaw, right? This is not code quality. This is design quality. It's about the interrelationships between the parts, not the individual parts. Most traditional tools that measure complexity in code these days are measuring the quality of individual functions or methods or lines of code, and they're ignoring the relationships, which I think matter more. So in principle, what are we looking at? We can use graph theory to reason about the structure of a code base, right? Ideally, you want a system to have good code quality, like we've seen before, but also to have maybe the concepts of layering, maybe the concepts of modularity, where you have high degrees of cohesion and lower external coupling, and APIs wrapped around things. We can talk about reuse. We can talk about having a hierarchy. So there's a top and a middle and a bottom in your system. These are all things that allow human beings in an organization to function. Because if I have a code base that's so complex that you need an IQ of 400 to understand what's going on, I want to carve it into 4 separate parts so that now I can have 4 teams of people with IQs of 100. And to the extent that that breaks down, now I need to have everyone having IQs of 400 again, and that's when they make mistakes, and that's when they're slow, and so on, right? So we can detect using static analysis and graph theory the difference between whether your code base looks like that or that. Unfortunately, 80% of the time we find that code actually looks more like the unhealthy one than the healthy one when we do scans to some extent or another. And so we can use graph theory to detect these places where the ideas of having a hierarchy of modules has broken down. Where do we have these upwards facing links in a graph that tie it together in a circular knot that we, in our research, call a core? So we can detect these cores, these large cyclic groups of files inside a code base. And we've found systems that have had tens of thousands of files all wrapped up inside cores, and those are the kinds of systems that people haven't been able to get to compile for the past 3.5 years, right? And that's, we've found some of those. But core, we start to detect a statistically significant uptick in defect density when a core becomes, maybe a size of 30 files or more, 20 to 30 files or more. So these are the kinds of things we can detect when we're reasoning about the design health of a system. We can combine that with other measures of code quality to do statistical analysis as to complexity and why it matters from an economic standpoint. Just a brief aside, this also matters from a cloud computing perspective. If you have a healthy monolithic application, it's easy to break it up into microservices. And if you have a tangled mess, it's very hard. So we can estimate the degree of difficulty of migrating. And also, if you care about cybersecurity, if you have a modular system with tight APIs, then you have a small attack surface area. So you care about these principles for a lot of reasons. And this is our one fancy animated slide that the intern did this one. That's good. I'm going to introduce a little bit of a new notation that's the same information that you just saw, but it's a different way of reasoning about graph theory. Have any of you seen a square matrix representation of a graph before? Anyone? Okay. Wow. That's a lot of you. All right. My audiences don't usually have that. So if you look at the upper left-hand picture, traditional graph diagram, if you were going to draw the architecture of a code base on the wall or on the whiteboard, you might say I have component D depends on component C, and component C depends on A and B. The way to read the square matrix is you take those nodes and you assign them an order down and across, and then you put a dot in the matrix at C comma A if there's dependency, of C on component A. So C depends on A, C depends on B, D depends on C. We've also filled in the indirect dependencies because those matter too. It's possible to break something indirectly, not just directly. Now I'm going to show you one picture to explain why this picture matters and how it represents almost all the things you care about from a software architecture or a complex system architecture standpoint, right? If I have this picture and I have, it represents a code base with maybe 6 components, A through F. And each one of those components has source code files inside it, right? So if that's true, then look up the C column and across the C row, and you'll see a box along the diagonal, right? That box represents a module. All the X's inside it are dependencies between stuff that's all inside component C. that represents high internal cohesion inside a software component. One measure of modularity is the extent to which I have x's inside those boxes versus outside those boxes. So I can just count x's, and that gives me a measure of modularity. You can also look at the vertical stripe. Here, let's say A. The way to read this is everything depends on A. So A is a utility, right? A is heavily reused. We like that. That's good from an economic standpoint. It's good from a quality standpoint. We have a control element, F. F might be main.c, right? F is your browser. A was your printf or something. We also see that all these x's are below the diagonal. The only way that you can order this picture so that all the x's are below the diagonal is if you have a hierarchical system, right? That basically tells me that those components depend on each other from top to bottom. The only places there are circular interdependencies are inside components, right? Above diagonal links in this picture, actually, let me just go back one to show this off. Note that there are no dots above the diagonal in this picture. That's only possible because this is a directed acyclic graph. There's no ordering of A, B, C, and D that would allow me to get all those dots below the diagonal unless all the arrows flowed in one direction from top to bottom in that system. So that's a visual diagnostic of hierarchy, right? So the fact that I have all of those x's that are not inside boxes below the diagonal tells me that these components depend on each other in a hierarchical fashion. If you're into Linux, it's Debian RPMs all having dependencies on each other, but not having circular ones or RPMs. Now, again, when we scan code bases and we draw these kinds of pictures, 80% of the time we see pictures. We ask developers what they actually have in their code base, and they draw something like the picture on the left there. And when we actually scan the code base, we find that it's really the one on the right. And those are not two different teams. That's one large development team, and they're constantly tripping over each other and fighting with each other and pulling their hair out. And so, we can measure all of these things, and we can reason about, what is the extent to which this thing is well designed versus the extent to which it's broken down. And I talked about these cores earlier. We can highlight the regions in the code base where there are these large cyclic groups tying systems together. And effectively, that's one large module, but it's got 760 files wrapped up inside it and multiple teams pulled in. And it's a problem, right? So now we have ways of using traditional metrics to measure design quality and code quality. And we can use information pulled out of version control systems and issue tracking systems to measure defect density, right? So I can figure out how many patches going on inside a file are to fix bugs versus to implement features. We can do statistical regressions around developer productivity, right? So if Mary is adding lines of code to X file on Tuesday, and is less productive than the next release when she's in Y file, that is better, then we can, over time, run models to figure out the impact of complexity on productivity, on defect density, and so forth, right? This is the result of one of those kinds of studies. This is a large code base, billion-dollar firm, 1,000 developers, and we're looking at developer productivity and defect density across that system. And what we found is that in the parts of that code base where there was good quality from both a code quality and a design quality standpoint, those people were producing 20,000 lines of code per year after you controlled for a bunch of other stuff, right? When they were in the bad parts of the code base, they were only producing 8,000 lines of code per year, right? We can look at the individual effects of design health versus code quality. It turns out design matters a little more from a productivity standpoint, but they both matter, and they're roughly the same order of magnitude in terms of how much they matter, so you're going to want to focus on both. Here's another study. It turns out that developers, when they are in the worst parts of code base, they quit or they are fired at 10 times the rate of the developers that are working in the nice parts of a code base, right? Because your life sucks, you're sitting on top of a volcano, every time you make a change it causes another bug, you're constantly fighting bugs, and your manager is yelling at you all the time because your stuff's never being delivered on time. So you're being beaten up from both ends. There's plenty of reasons why you want a healthy amount of turnover in your organization, but this is not one of them, right? So this is another study that our team has done. Here's some others looking at safety critical systems. Turns out that in a safety critical system, when you looked at the good parts of it, less than 1% of it had to be patched after it went live, whereas 13% of those files had to be patched after it went live in the degraded parts of the system. And there are some other studies around cybersecurity as well. Here's an interesting one. This is looking at a successful refactoring that ultimately took a dirty platform like the one we saw in the video game and turned it into a healthy platform. And after that, what we see is a dramatic uptick in the rate at which that company can produce revenue-generating products on top of that product platform, right? So these developers are all decoupled from each other. The teams can work in an agile fashion independently. They can be on their own release schedules. They're not fighting against each other, and so they can produce a lot more. So this isn't just about cost containment or productivity. It's also about top-line growth for a company, right? So what can we do now with this information? We have measured code quality and design quality in many, many different systems in our research group at MIT and Harvard. We have statistically connected that to developer productivity, to defect density, to staff turnover, and other things of economic value. Now that we have these models, we can apply them. Given a new code base, we can say something about what's likely to happen on a new project that, in a code base that already exists, right? So here's an example of something that we did for a commercial firm, right? This is a schedule prediction tool, right? It turns out that if you measure the health of that code base in different parts, you can take the data that we gathered from other places, from this code base, pump it through the models built from other data, and say some things about what's likely to happen inside this system. So when we measured this system, we said overall, let's say you're developing a new 1,000-line of code feature. It's going to take you something on the order of 12 days to write that 1,000 lines of code. During that process, you're going to be introducing 48 lines of defect. It's going to take you 2 days to fix those bugs and gives you a grand total of 14 days to develop that 1,000-line of code feature if you're equally likely to be modifying any line of code in that code base, right? But if you look at the people who are working in those cores, those degraded regions of the system, that goes up to 26, 27 days is predicted, right? So if you are looking at two different developers and one seems a lot less productive than the other, maybe it's not the developer, maybe it's the code that they're working in, right, is sort of one of the takeaways here. Because often it's the system that causes these kinds of things. I'm not going to belabor this too much, but this is an ROI of refactoring tool. One of the hardest things to do in a software organization is to convince someone to give you money to refactor, right? Because Toyota is going to give me $2 million if this feature is out by Wednesday, right? All of our customers will leave us if these bugs are not fixed. But instead, I want to work on this magical third thing called refactoring, which isn't going to make anything any better, in terms of, from the standpoint of the business. Yet, ultimately, that's the continuous refactoring is the thing that's going to keep your organization, your code base healthy over time. It's like going to the gym, right? If you never go to the gym, you're going to be sitting fat on your couch eating Twinkies all the time, and eventually you're going to die of a heart attack, right? Well, going to the gym is like paying down technical debt. So what we're doing here is trying to make that salient. This is a tool that takes the same kinds of models we talked about and allows you to plug in, takes measures of your code base, predicts developer productivity and defect density based on that, and then allows you to say, well, what if we were at the 90th percentile in terms of quality in our system instead of at the 10th? How much more productive would we be? How many fewer defects would we have? And how would that translate into person hours or dollars? What is the benefit of this glorious future? Then we can reason about the cost of getting there by either rewriting the system or refactoring it. And if you can do that calculus, now you can go to a CFO and explain why you should worry about paying down technical debt, either inside a system or systematically across an entire portfolio. You can have a more optimal strategy around how to do that. And this is the kind of work that we've been doing a lot with the DoD. We've scanned 75 DoD systems, major weapon systems, major other kinds of systems I'm not going to really talk too much about. But we're able to get key metrics in terms of design quality, code quality, do predictions around what the business impact of that is going to be, right? If you are making yourself dependent upon a piece of infrastructure that's going to bite you a few years down the line. If you're paying someone to write that code and this is what they're delivering you, what does that mean? Based on that, a variety, we've scanned 75 plus systems. Maybe, I'd say in 3 to 5 of them, there were multi-million, if not billion-dollar decisions made based on the information that we provided. Because now all of a sudden you have the visibility to talk, have useful conversations between the managers and the technologists, and you're not just throwing good money after bad. Let me go on to this one. Here's an example of one of the systems that we looked at with them. What we found is that this was a system that was originally created in the 60s and is still under active sustainment. The story is that they built it in the 60s in Jovial. Then in the 1980s, they recoded it line by line into Ada, but they weren't willing to spend any money on improving the architecture. So they just said, we're gonna direct translate the Jovial syntax into Ada. So they preserved 20 years worth of technical debt in a new language. And then they got to about 20 years ago, and there was a new RFP that hit the street saying, we want a new system that does X, Y, and Z. Well, the system they already did X and Y. It met 80% of the functional requirements that were out there. So the government said, great, you meet 80% of the functional requirements, we're going to get this 20 cents on the dollar. Right? So they went with this legacy system. Fast forward to about 5 years ago, performance of that development organization was so bad that they took responsibility away from that group and they gave it to another group on the premise, again, that it must be the team or the leadership. Well, the new team couldn't maintain it either. So then they sent everyone to Scrum Master training. And they said, well, you guys aren't getting new releases out, you're not getting any new features out, you're going to have to learn how to do stand-ups and sprints and things like that, because clearly that's the problem. When we scanned it, it was, the other thing they do is they put it through some tools that measure code quality. And those tools came back and said, this thing is fine, clean bill of health. And when we ran our code quality metrics on it, we had it positioned at around the 69th, 70th percentile. So nothing that would explain the fact that it hadn't compiled in 3.5 years, right? And this is a system that's defending us right now, and that they're using a version from 3.5 years ago. But when we scanned the design quality, we found that at the time it was the most challenged system we'd ever seen. Right? There were 11,000 files circularly interdependent upon each other in one way or another, directly or indirectly. So now we're doing predictive analytics. The models said that for every $1 million spent on continued development and maintenance, 860,000 of those would be wasted. Models said that predicted that 60% of labor would be spent fixing bugs, which doesn't sound too bad, except for the fact that they're so unpredictable when they're fixing bugs and when they're developing features that they're just bad on both fronts. And that there would be an unacceptable risk. And based on this, again, they make the decision to cut the cord. What other things can we predict out of this data, right? We're predicting that in the optimal code bases, it would take 14 days to develop a new 1,000-line of code feature. The blue part of this bar is the time spent writing those 1,000 lines of code. The red part of the bar is time spent fixing the bugs that are introduced or exposed during that process. In this code base, that's 83 days. So again, they were sending people to Scrum Master training and telling them to do 2 or 3 week sprints when a 1,000-line of code feature is going to take you 83 days. That is not a sprint, right? You can't do agile software development in this kind of system, right? So there is hope, right? We have developed tools to use, again, using graph theory to help people optimally attack and decompose the system to make it much more modular. This is an organization we're working with where we have provided these tools to them, and after about a week they were able to reduce that core size by about 15%, right? And that work is ongoing. Now, this is an IEEE article that was written based on a lot of these experiences with the DoD about how modular architectures can make you agile in the long run. Ultimately, it means that you have to manage the architectural health of a code base as it grows if you want to continue to be agile. Right now, people, when they're talking about agility in software development, they're focused on development process. I'd say you also need to be equally focused on having an agile architecture. Otherwise, you're just going to be making crap faster, right? So that's definitely one of the learnings that we've seen. So let me just kind of end by saying who I am. So I'm the CEO of a company called Silverthread. We originally started about 15 years ago as a research group out of MIT and Harvard, and then started commercializing this technology about 4 years ago. And we've been helping both commercial organizations and government organizations figure out how to better manage their technical debt and have better conversations between technologists and business people so they can make better choices across their portfolios and in their systems. And this is our team. So I'll be quiet and take any questions you guys have.
Part of the room.
Gentleman in the back, okay? Or, well, are you're gonna use the mic?
You can be next.
Hey, thanks for the talk. I'm curious, do you have any strong feelings on microservice versus monolith in terms of like smaller organizations, larger organizations, development velocity?
What I like about the microservices is that they naturally enforce the principles that you would want in a code base. We're measuring systems where there were no guardrails in place, and I think by their very nature they put guardrails in place so you can't get yourself in the kinds of trouble that we see here. So I like that. Does that make sense?
That was a great talk. Thank you so much. So it looked like one of the metrics you used had something to do with the McCabe metric.
Yeah.
And then I'm just wondering, did you develop software to be able to visualize these great illustrations that you showed about efficiency and inefficiency?
Oh yeah. So your first question was about McCabe. McCabe complexity, also known as cyclomatic complexity, is a measure that was invented in I think 1979 by a guy named McCabe, that looks at the number of paths through a function or a method or some kind of other executable block of code. And I like that metric a lot. It's a code quality metric because, again, it's measuring the health of an individual unit within that system, that being a function or a method in this case. But every time we've measured it, it has a very strong correlation with defect density, right? An incredibly strong one. McCabe scores of, if you get a score from 0 to 10 versus 10 to 20, you get a doubling in defect density. And if you look at a score from the low bucket 1 to 10 versus 20 above, you get a tripling in defect density. So we use that one in our models. There are thousands of software metrics out there, and most of them have no empirical sort of validation or basis, other than some person made it up and thought it was a good idea and then is sharing their opinion with the world. But McCabe's a great one because it matters. I think the second question was around tools. So we have developed tools first as a research group and now commercially to scan code bases, to mine information out of them. Also, we can pull information from version control and issue tracking systems to look at outcome, pull together outcome information, do statistics around that, and then do the predictive stuff to generate these reports that allow people to reason about both, to have a deep insight into the design health of your system and also the cost of ownership consequences of it. So we have some different products that go on top of that platform, but that's what we've been doing.
In all of your empirical research you've done on software and architecture quality, have you found any deviations or differences from what people traditionally say is good software quality?
Well, many of these network metrics we invented. One of the people are generally much more focused on the code quality stuff. The two professors who kind of were doing this research originally, they weren't software people, they were finance people, right? So they were coming at this with a blank slate, and they would go into development organizations and they were trying to do surveys to ask about, what they were asking about, which different agile methods influenced productivity or quality or something else. And people, when they were talking to them, kept saying, well, yeah, but it's the architecture, it's the architecture, it's the architecture. And they said, okay, well, how do I measure that? And all of the engineers would say, I don't know, it's just the architecture, right? So they had to come up with these ways of measuring the architecture using these visualizations and this kind of graph theory. And at first, they had a graduate student who was coding this up, trying to find the modularity that all the engineers told them was in their code bases. And for an 18-month period, they thought that their algorithms were wrong because they could never find these nice modular systems the engineers were telling them were there. And after 18 months, it dawned on them that these engineers have no idea what they're talking about. It's them, not us, right? So, so I'd say that's certainly an insight that was interesting.
So have you been able to run, so the case studies in the, are great, most interesting. Do you have any anecdotes or case studies on large open source projects?
Yep. Open Robotics Foundation makes the robotics operating system. So the robotics operating system, Debian-based system that has a platform that's maintained by an open foundation, but then thousands of plugins that get contributed by different vendors, who have different chipsets or different robot arms or different universities. And they were interested because they wanted to know, if something crashes or burns, it's our reputation is on the line, right? So we scanned their platform and found that it was very clean from all of these perspectives, and that was great. But then we scanned the code base with their platform, their million lines of code, and another 12 million lines of code that made up the plugins that were being produced by vendors in their ecosystem. And we found one vendor that was producing code that I would not want to have a spacecraft relying on, right? So this was very important to them because their reputation is going to take a hit, whether it's their platform or whether it's someone else they're letting into this ecosystem. And so now, I'm not sure if they can kick them out, but that's certainly something that's interesting. Another thing that we've studied, I think a paper written a while ago, was a systematic look at open source versus commercially developed code. And they looked at 6 pairs of systems, right? So they look at Linux versus Solaris when Solaris was not open source, right? It was developed by a company, and a bunch of other pairs. What they found is that open source was systematically better than code developed by companies. And one of the reasons that might be is that if you have constrained communication channels between people because they're on different continents or they're in different organizations, it's impossible for you to build a system that's a giant tangled mess. Because in order to resolve that, you've got to have everyone in a conference room together, right? So you just can't get yourself into as big a mess because of the organizational constraints inside those communities.
I was going to, having been a CIO in several organizations, I'm wondering which companies or industries are primarily using your tools to look at their portfolios?
Mm-hmm. We've got defense is interested, federal as well. I mean, at least at first, but we've also gone into aerospace industry, travel industry. Mergers and acquisitions, right? So due diligence. You're going to buy a software company. You want to know, you don't want buyer's remorse, right? And now we're working with companies to actually help them fix it. We didn't start off developing the tools to fix the problem. We started off with the tools to illuminate the problem so that they would know what they wanted to fix. So there's a lot of different. There's no code is code, so it doesn't really matter what the application is in a lot of ways, actually, for what we're doing.
Hi, I just wanted to ask, how amenable has the government been to actually updating code just for improving architecture? Because in the past, we've had a lot of trouble convincing them.
Oh, it's a huge problem. What I will say is that, I can tell you a few stories, that kind of explain why I think this approach is actually pretty powerful. There was one group that we worked with in the government where they had been fighting for 3 years about, one community of people in one Air Force base thought this system was the best thing ever, and the other one thought that this thing was horrible, right, and wanted to end it, right? So they were fighting for 3 years, and everyone assumed everyone was being stupid or political or being bribed or whatever it was, right? Well, so we went in and we scanned the code, and it had a JavaScript front end and a Java back end. The Java back end looked fine. The JavaScript front end, had problems. Well, it turned out all the people that hated it worked with the front end, and all the people who loved it worked with the back end. And so then they kind of turned and said, okay, I'm not stupid and you're not stupid. And within a month, they funded the complete rewrite of the front end, right? So having that kind of information allowed them to actually come to a better conclusion. There have been multiple systems that they've decided based on this analysis to do complete rewrites, where it might be $100 million or in one case $1 billion endeavor, but you need the information to do so, right? And that's what they were lacking. Because if you're jumping from post to post every 2 or 3 years, it's on your watch, you just want things to go smoothly, so you're just going to kind of let it ride, and you sum that across lots of people, and you go for 60 years with a system that's falling apart.
I think we have time for one more question if it exists.
Yes, thank you for doing this. Can you comment on the impact of the dimensions of time, as in how much time did it take to write a piece of software? Is it like a year, or has it been 10 years? And most especially people, that is, how many different people were involved in a piece of software versus, a tight team versus, there was a revolving door and there's many different developers that came in and had to rewrite something. Is there any data that indicates benefits, or is it something that is really not relevant?
Benefits of having teams.
Benefits of having the longer that you spend doing a software project, then it's bound to do this, or the more people that are involved, different people, not as in quantity.
It's okay. So one of the problems with technical debt, right? So I guess the idea of going slow to go fast, right? If you measure twice and cut once, that's good, but measuring twice takes more time. And so, is that kind of what you're getting at?
I think the question is, if there's a lot of turnover in a team, does that code look messier, or does it look better because more people are getting in and sort of cleaning it up and doing it the way it should be?
I don't have any data on that. What I will tell you is that if you are in one of those really bad parts of a code, one of those giant fur balls in a code base, you have longer learning curves and you have faster attrition, right? So you can get yourself from technical debt into technical bankruptcy as these things grow over time, if you have enough attrition that no one who developed that code understands it anymore. So that's certainly a challenge. There have been some systems where again, let's go back to that open robotics example where the platform was clean and most of the vendors were behaving well, but there was this one vendor that was a bad actor. Well, so we go to the organization and say, okay, why, what's going on? And they said, well, that organization always ships their code late. It's always got problems. And I said, okay, why do you think that is? And they said, well, they go through these cyclic layoffs, right? They're constantly hiring people and firing people and hiring people and firing people. And in the downtimes, what they do is they hire a bunch of college students and graduate students to come write the code. And so you've got this sine wave of professionally trained developers, and you got these students filling in the gaps, and that resulted in this massive core.
Awesome. Well, thank you so much. That was super informative. You lost me somewhere along the way, which is good. That's what I look for as a non-technical person. And then we've got one more session before break, and then you might be able to attack Dan during the break if he's around.
Thank you.